Hello everyone, this is Professor Kuehn, and what I'm going to do is I'm going to, in this lecture, describe what we mean by a free body or a force diagram. This is going to be necessary in order to carry out your force and rotation lab. So let me turn off my webcam. Okay, so what is a free body or a force diagram? Basically, the idea of a free body or a force diagram is to sketch all of the forces that are acting on a particular object. So for example, if we have a, let's say a tire, and there are three people pulling on this tire. So one person is pulling on the tire in this direction. That's the force that maybe John is pulling on it with, and somebody else is pulling on the tire in this direction. Maybe that's the force with which Matthew is pulling on it, and somebody else is pulling it on this way. That's the force with which April is pulling on this tire. Okay, so technically speaking, this it looks like a force diagram because we've got this object here and then all the forces that are acting on it. But usually force diagrams or free body diagrams are simplified. So you don't have to actually draw the object. You represent the object by simply a dot that is supposed to represent our tire. And then we draw an arrow for each force that is pulling on it. So this would be the force with which John is pulling on it. This would be the force with which Matthew is pulling on it. And this would be the force with which April is pulling on that. So that's an example of a free body or a force diagram. We're going to be doing a lot of these force diagrams over the next few weeks, so it's good for you to get used to them at this point. The idea is each of these arrows, the length of the arrow is supposed to be indicative of how strong that force is. So if this is a very strong force, it's going to be a long arrow. If it's a weak force, it's going to be a short arrow. So you've got the length of it that represents how strong the force is, and the direction of the arrow represents the direction that this force is aiming. Okay, so each of those arrows is indicative of both a strength or a magnitude of the force and a direction. Okay. All right, so having said that, now what we're going to do is we are going to draw some free body diagrams for the force and rotation apparatus. So what I'm going to do is let me get rid of these for the moment. Let's import an image. Let's add an image. And this is a picture that I took. This is awfully big. Let me scale it down a little bit. This is a picture that actually Professor Schindler took this picture. And what I want to do is this hanging mass really, in fact, kind of looks like a force diagram, right? So let's go ahead and draw arrows on this to indicate what the force diagram looks like. Okay, so I'm going to draw a dot here that represents the mass. And there are four forces that are acting on this mass. So the first force that's acting on it is, let's draw an arrow like this. This is the force with which the spring is pulling on this mass to the right. In addition, there's another force. There is a force, I'll call this force 1. That's the force with which this string is pulling upward. Then there's another force. I'll call this force 2. That's the force with which this string is pulling on the mass. And finally, there's another force. This is the force of gravity that is pulling downward. So we have four forces that are acting on this mass. Okay? Now, notice a couple of things about this. First of all, we can say right away that because this mass is not accelerating, that the sum of those forces must be zero. How do we know that? Well, we know by Newton's second law. Newton's second law says that the change of momentum of an object is equal to the force acting on it times the amount of time that the force is acting on it. Okay. Now we know that this object is sitting still. This mass is sitting still. Therefore, the change in momentum is going to be zero. It's not accelerating. Its momentum is not changing at all. Therefore, the total force acting on it must be zero. So the net force acting on the mass must be zero. Otherwise, its momentum would be changing. That is, it would be accelerating. Perhaps that's more obvious from writing Newton's second law in a slightly different way. We'll come back to this later. So if this is new to you, don't sweat it. Force equals mass times acceleration. These two ways of writing Newton's second law are actually equivalent, as I mentioned in a previous lecture. And again, I'll come back and explain how these are related shortly. But if there is zero net force, if all those forces somehow cancel each other, then the acceleration is zero. Or conversely, if the acceleration is zero, we know that the net force acting on it must be zero. So what does that tell us specifically about these forces? We have these four forces on it, and two of them are horizontal in the x direction. If I were to kind of draw an x and y axis like this, here's x, here's y, the forces that are acting in the x direction must exactly balance each other. So the spring force must be balancing this force 2, right? So since the acceleration in the x direction equals 0, then the spring force must be exactly equal to force 2. Otherwise, there would be a net force or an unbalanced force in the x direction. Okay, so we're using Newton's second law to deduce that this force here, the spring force, must be equal to the string force, force 2. Likewise, in the vertical direction, since the acceleration in the y direction is 0, that implies that force 1, the force with which this string is pulling up on it, must exactly balance the force of gravity. Okay, so again, we're using Newton's second law to deduce the relationship between those forces. Okay? All right. Let me leave this at this for the moment, leave that here, and I'm going to come back in the next lecture and talk about Newton's third law.